I'm Abby Odell, president of our Rocky Mountain SCTE chapter, and I'm super excited to welcome Keith Auzenne here today to talk to us about the evolution of our network, a little bit about the past and the future. But before we jump into that, I want to share a couple of things with you about our fabulous chapter. So our mission here at SCTE Rocky Mountain is to be the best chapter in the world, and we really want to give back to our cable community and support our members by helping them grow and develop in our industry. And just a shout out to our fabulous board. We got a lot of great awards last year for our work, not just in training and development, but in a lot of other areas. And we owe that to our members like you who join us on these sessions. So if you're wondering, how do I become a member, or how do I renew my membership, or how do I even check if maybe I am a member? For our Comcast folks, there's actually a custom process on your portal for Comcast. So just make sure that you select Comcast as your primary organization, and that processes the routing for your membership. For others, you can log in at any time through scte.org and check your My Account settings to view what your status is. Do you need to renew and view invoices and all that good stuff. If you ever have any questions or issues with that or need help with renewing, reach out to any member of our board and we'd be happy to help you with that. Now, as far as benefits that you get for being part of our awesome chapter, we, like other chapters, give you access to SCTE's suite of certifications. So the cool thing about certifications is that it's industry recognized. So it transcends just your particular company, and other MSOs, other organizations within the cable industry will recognize that skill, that knowledge that you bring if you have obtained any of the certifications offered by SCTE. So it's a great way to move your career forward and a way to show your chops and what you know about all of the fascinating technologies in our industry. Another cool thing about it that you may or may not know is that the Rocky Mountain chapter has a certification incentive program where we will, if you pass the certification exam and you have out-of-pocket fees, we will actually help with that cost. We will reimburse those fees and then give you an incentive reward. So what's stopping you from getting an awesome certification with SCTE? We will even back you up and make sure that you don't have anything out of pocket. Speaking of certifications, what certifications are out there? You may be asking, well, SCTE's got everything. I mean, basically anything from installer level coursework like BPI, BPE, BWS, so installer frontline level, the whole way up through head end and engineering and everything in between. If you ever have questions about that or you're interested to know more, you can always check out SCTE's website at scte.org, or again, reach out to any member of our fabulous Rocky Mountain chapter. If you're wondering, how do I connect to those folks in the Rocky Mountain chapter? We have a great presence on social media. Hopefully you're already connected with us, and this is not news to you. But we are on Facebook, we're on Twitter. You can email us at any time. We have a website. Lots of great stuff that you can find on the website, including access to things like our upcoming events and how to contact us there. Speaking of upcoming events, just a quick plug for one that's coming up before we hear from Keith. We have our inaugural in-person event after the last 2 crazy years coming up at the Ridge at Castle Pines Golf Club. It's a 2-day event. So the first day, part 1, is on June 21st, and it's in the afternoon, evening. That is cable games. So you know and love cable games. So cable games. There's also going to be a leadership panel interview where you will get to hear from some leaders from some of our industry organizations, as well as a mixer networking event where you can connect with other people within our chapter and other vendor partners and other companies. And then the following day is our golf event. So if you need to know more about how to sign up for that, as you just heard, you can go to our website and get connected with us there and get signed up. So we would love to see you there. But now, you don't want to hear from me, you want to hear from Keith. So Keith is a principal engineer here at Charter, and he has been in the industry for 44 years. So he started back in 1978, and he started out climbing poles and in trenches out on the front line, did installation, did construction, and he worked for Daniels Cablevision. So in that role, he worked his way up through the ranks into the role of lead tech, but then got really into learning more about our industry. NCTI courses, you guys are probably familiar with NCTI. Also other organizations like GI, Phillips, Scientific Atlanta, all of the classes that he could take to up his skill level there. So he moved into engineering roles at Group W and Century, and then moved into a construction manager role for Century and Insight, and he oversaw all of the design and construction for rebuilds throughout all of those systems. So he also, pretty cool thing here, in 1997, he founded Centerpoint CAD Designers from out of Phoenix, Arizona, and operated that company for 16 years. So after that ended and he wrapped that up, he moved into construction with Poly Construction, Bridgepoint, and subterranean directional drilling. Also has been with Wave Broadband and managed fiber to the premises or fiber FTTX services there. So he's now with us here at Charter and is a principal engineer, and he's responsible for developing and designing our HFC network. But he's going to be telling us a little bit about the evolution of our network. And Keith, I'm going to pass it over to you.
Well, thank you so much, Abby, for that wonderful introduction. And hello, everybody. I do want to extend a warm thank you to Nick Segura, Justin Stiles, Abby Odell, and Andrew Goff for inviting me to speak and have the opportunity to do a presentation. It's an honor and a privilege to speak to such a wide and diverse group of people. I can only imagine that there are some of those who have been in the industry for quite some time, and there may be also some on the call who are relatively new to our industry. I thought this would be a kind of a cool way to show where we've been over the past 45 years, where we kind of started. It actually started prior to 45 years, but it got real serious back, I would say, in the mid-70s. And I thought it might be kind of nice to show where we were and how we got to where we are today, which is pretty interesting. So yeah, so as I said, here's 45 years of network evolution, kind of like, I guess you could say from the Model A to 500 horsepower Mustangs. We've really come a long way in 45 years in our industry. So what is network evolution? It's the gradual development of something, especially from a simple to a more complex form. I think that describes us pretty well. We were very simple 45 years ago. I would say we're fairly complicated today. I know within our own team of people here at Charter, we bounce a lot of things off of each other, and I think each of us learns something every day that we didn't know the previous day. So it's a very exciting industry to be part of. Simply put, the evolution of a network is to increase its overall performance, its capability, increase its bandwidth, its data capacity. We like to increase our, achieve higher transference of speeds over time. And we kind of have to do that. As we know, there are a multitude of communication companies, and we're all striving for that customer. A lot of the demand comes from our government, possibly our military, small and large business, residential, ever-increasing mobile markets. That's an extremely competitive market, as well as Wi-Fi access. It's nice to know that you can grab a Wi-Fi signal almost anywhere you are in a fairly dense city. So a lot of that rise and depends on our backbone networks. What's involved in a network evolution? A lot of us engineers and technical people, we hear about our companies from time to time talking about doing an upgrade. That's a big word. There is a lot behind an upgrade. It goes way beyond just the technical aspects of what we may be specifically involved in some portion of the technology, improving the technology, understanding the technology, and so forth. That's a huge factor. But beyond that, we've got these bullet points on the left that are oftentimes other departments within our companies pursue these bullet points, and they have to do what we call a market study just to see if is this upgrade that we're proposing to do, what's there to be gained? What are we going to gain by it? Are we going to increase our bandwidth or our data capacities or our speeds to the point where our customers will be attracted to that? Are they willing to pay possibly a little bit more per month as a result of the cost to do these upgrades? So behind all these upgrades are these bullet points. The electronics and cables and material costs are tremendous. Engineering and construction costs, route planning and permitting. I mean, just to do some simple, what we call potholing along the side of a right-of-way has to be permitted. We have to pay companies and people to go out and do that permitting. There's route planning. Are we going to stay on the existing routes that we're already on, or are we going to add additional routes that we have to apply to be in those right-of-ways or be on those pole lines, or possibly enter an easement that belongs to the power company or the phone company? This is all heavy-duty planning and permitting. Project management. There's a ton of project management that goes into these upgrades. I can't even begin to tell you how many people are involved in that and how critical it is to do the phase planning. The phase planning would be, what markets are we going to approach first? What nodes in those markets are we going to approach first, second, and third? There's always an order of events, if you will, that has to be pulled off and make sense and follow a particular flow. So there's a lot of planning that goes into place. Some of us are involved in product testing and evaluation. Are these new electronics performing the way we need them to perform? Are there any issues with these electronics where we have to go back to the manufacturer and ask questions, or in some way, possibly have them improve these electronics? There's a lot of evaluation that goes on in that regard before we even know what electronic we might use. So there's a lot of work that goes in behind that. Once we decide on a certain type of electronic or a certain bandwidth or a certain criteria, we then design, model, and we implement it, and we perhaps drop these new electronics into modeled networks to see how they perform or what they do. Is this going to accomplish the goal that we set out to accomplish? Are we going to reach what we thought we would reach with this whole network evolution idea with these electronics? Then we boil down all these bullet points above this bottom bullet point, trickles down to dollars and cents. And we're talking about, in most cases, we're talking millions of dollars to upgrade a sizable amount of broadband network. So what is the payback on that? That can be a 5-year, a 7-year, a 10-year payback. When do we recoup the costs that it took to build all this stuff, and when can we realize a profit? We are a profit-driven business, and we do have to not only recoup our costs, but also realize a profit. So to say network evolution, and we're going to expand from, let's say, 870 megahertz to 1 gig or something similar in the past, we're talking a lot of money and a lot of planning. So I just wanted to pop back and show where the network evolution kind of started 45 years ago, and sort of the incremental steps we've taken over those 45 years. As I said earlier, in the mid-70s, we were around 212 megahertz. These systems were only one-way capable, meaning they were just a downstream from the head end, carrying a very small amount of video channels. So we had audio and video. And these were also the systems where we started to realize that we needed what's called a closed coaxial system. I'm going to jump one slide ahead just to show what I'm trying to talk about here on this first point. On the left side of this slide is what you see is called a twin lead. It also is called ladder line. It's even been called open wire. If you were close up with some of this stuff, these spacers put these wires about 3 inches apart, and that is the transmission of your RF. That worked not too bad when you only had 12 channels back in the mid-70s, but it didn't take long for the FCC and the FAA to say, hey, we have to stop radiating RF all over the place. It's interfering with other forms of transmission. It could possibly cause problems in aviation. So there was a huge push and a big demand to go back to closed coaxial networks. So that's when we started really paying attention to this. We then migrated from 212 to 330. These systems were still 30 volts. They operated on only 30 volts, 37 channels in this case. We then went up to 450 megahertz. We thought we were really expanding. I remember the days when 450 modules came out, and we thought, wow, this is really something. We also went from 30 to 60 volt systems, and we increased our bandwidth so we could carry up to 54 channels. We were still sub and low split upstream at that point, meaning a 30 upstream or 42 megahertz upstream. But in those days, that was considered pretty state of the art. We were then starting to do a two-way system. We had, in other words, a bi-directional two-way cable TV system. Again, this was a big deal. So this is part of our evolution, and it was actually a pretty big step. When we got to 60 volts, we now had much more efficient use of our power, more efficient use of our power supplies. We could load them a little heavier. The actives ran much better at 60 than they did at 30 volts. So we were really making some progress when we got to 450. So that went along for a few years, but it really didn't take long for somebody to say, we need to get out to 550. We need to increase our bandwidth. We did that. But the other thing that happened when 550 came along, that was the first introduction of optics. And let me tell you, that was probably around the mid 80s, early to mid 80s, I would say. That is still today one of the biggest improvements in broadband history. When we went from purely coax to the introduction of fiber optics and nodes as we know them by today, that was a huge step. And so, as you guys know, we still rely on that same technology, that same architecture today. So we launched from 550 to 750. We increased our channels. We still had a low split upstream, but we had a lot more on the downstream. We then went to 870, increased to 132 channels, still kind of a low split upstream. When we got to 1 gig, another big step, we increased our channel capacity significantly, but we also went to what we call a mid-split upstream, meaning we have more upstream capability now for the return path. So that was a big deal. We then also started playing around with the idea of what we call remote PHY. That's a huge thing. We're going to talk about that in a few slides. I don't want to try to go there right now because it's quite a bit, but we will get to that, what is remote PHY, in a few slides. But as you guys are well aware, we are now at a 1.2 gigahertz high split or mid split, depending. This is huge. This is another giant leap. We went from 1 gig to 1.2. We increased our downstream capacity. And if we're at high split now, we've really increased our upstream capacity as well. So we've really expanded our usable bandwidth. We are also introducing 2 new acronyms here that some of you may have heard being thrown around, OFDM and OFDMA. OFDMs, or orthogonal frequency division multiplexing, and orthogonal frequency division multiplexing access for OFDMA. This is generally used in the high split upstream architecture. With 1.2, we're also looking at what we call remote MAC-PHY. Very similar to remote PHY, but remote MAC-PHY is just a little better, and we're going to talk about that as well. And as you've probably been hearing, a lot of providers are talking about experimenting with 1.8 gigahertz ESD. That's kind of where we are today. We're focusing on that, trying to understand the technology around it. It's exciting to be part of that. And so before I move off this slide, I just want you to take a step back and take a look. We went from 212 megahertz 45 years ago to 1794 megahertz or 1.8 gigahertz today. That is a huge, huge step. So I've been talking quite a bit. Are there any questions on anything we've covered so far? And by the way, I guess I meant to mention in the very beginning, if anyone has a question, please put it in the chat window. Justin is monitoring that, and it might be good to do that while we're kind of fresh with some of the slides. So anybody wants to ask a question, go ahead and fire away.
We got one. Conduit placement. Why didn't we bury conduit in plant bills in 100% of underground areas?
Well, that's a good question. Some MSOs, to be honest with you, back in those days, they didn't want to expense putting in the pipe. That's the simple answer. I actually worked for an MSO back in those days for a short time where they didn't want to expense the pipe. They thought the coax could take being direct buried. We know today that was not a great idea for all kinds of reasons that we really don't need to go into. So what that means today, unfortunately, if we have coax that needs to be repaired or replaced, we have to pretty much dig it up to get to it to fix it, and that's a pretty huge cost. But that's kind of like hindsight. Boy, if we just knew then what we know now. A great question. Okay, I'll move on.
We got one more.
Okay.
What bullets would microwave fit in? 330, 550-ish, or do we still see it being used today?
Say the first part of that again, Justin.
What bullets would microwave fit in?
What bullets would microwave fit in? Well,
Travis, can you elaborate on that, or do you know what he's talking about?
Well, all I can say about microwave, I did work for a company where we were about 100 miles from Los Angeles in terms of distance, and our transmit, one of our towers was a microwave tower in Los Angeles, and we did receive microwave 100 miles away to our head end, which it had to be bounced off of a few different repeaters before it got to us. One of the microwave receive dishes was up in the mountains it was about halfway between us and Los Angeles, and they would shoot that microwave signal to that microwave dish, and then it would bounce off of that dish and head our way for another 50 miles or so. And it worked great until it was wintertime and it snowed. and when the dish got snow on it, we had to call, we had a guy, I think he worked for the fire department or something up there, and he would go up there and clear the dish for us and clear up our programming. But as far as microwave goes, it's still used today. It's a very good means of transmitting signal. It's a very, very high frequency. It worked quite well, but it can be interfered with weather conditions, trees, buildings, that type of thing. I hope that answered that question. So I just wanted to jump back a little bit again, guys, just so you can really kind of appreciate where we are today. Again, the ladder line on the left side, and on the right side, tube amplifiers. Probably anybody that's only been in this, and I say only, been in the industry for 20 years may not have ever seen these. I do remember as a technician, if you had a service call or an outage or something at night and you had to roll on that call, one of the best ways to determine which one of these tube amplifiers has quit working that may have caused the outage was to open the weatherproof can that these things were stored in and look to see which tube was burned out. It was a pretty surefire way of saying, yeah, I think I found the problem. So we literally used to carry around, RCA used to make them. They would make these tubes for these tube amps and replace the tube, call dispatch. Yep, it's back on. Okay, now I can go home. So it's kind of funny. But you know, this is where we started. So this is very interesting, and I have a lot of respect for these electronics. Everybody was trying to figure it out. And look where they led us to, you know, nothing but appreciation, respect, and admiration for the people that built these early actives. So this is an example of a couple of 330 meg amplifiers. This is what they used to look like. And when you look at these, you know, they look old, and they are old. They're a little beat up. I suspect these are probably in a cable museum someplace. But when you look at these guys, they really kind of started the clamshell amplifier we have today. There's a lot of resemblance here. So again, you know, hats off to these people that started thinking about solid state actives. It was time we were replacing, getting rid of the twin lead with coax. We were trying to get rid of the tube amps with solid state. So this was actually a pretty big improvement in how we amplify our RF. And again, if any of you are on the call that have been in the industry for a while, you might recognize this guy. This was what I refer to as the workhorse of the 70s. This was a Vicoa line extender, and these things were hardy. I mean, they just kept running. They were like that old Ford or Chevy pickup that just won't quit. And we used these exclusively back in those days because they were very reliable. They had a reasonable amount of gain. They're a little bit, the noise figure was not too good back in those days. But again, you know, you're only running 12, maybe 37 channels. So the channel loading wasn't too bad. And by today's, you know, measurements and performance and distortion numbers, they're not very clean. These were kind of a dirty little amplifier. Back in those days, they served the purpose. So, you know, you got to start somewhere, and these things were very, very dependable.
Keith, we had another question. Can you speak towards a 60 volt system versus a 90 volt system?
Sure. When we went from 30 to 60, we realized that we made much more efficient use of our AC. We realized that the modules run much more efficiently at 60 than they do at 30. We realized we could power many more actives off of a single power supply, as long as that power supply was now 60 volts. So the same approach to 90 volts. The actives today now run much more efficiently at 90 volts than they can at 60. They consume less current. Anytime you feed an amplifier a little bit more AC, it consumes less current, so there's less load on the power supply, meaning you can now add more actives into a network, power them up at 90 volts, and your power supply will realize slightly less load per active. The loads on the new power supplies go, you know, all the way up to 22 amps, which is pretty high. And true enough, you know, the further away you are from a power supply with your electronics on coax, the further away those amplifiers are, I should say, the lower the voltage becomes. It's called voltage drop on coax. So the voltage drops. It starts out at approximately 89 volts. After it's gone through many cascades, we're now down to the high 40s in terms of voltage, maybe the low 50s. And now these line extenders and those type of amps that are probably near those end of lines on coax are pretty current hungry. They start to consume some current. And so at that point in time, it's time to cut your losses on that power loop and possibly look at, you know, putting in another power supply. But anytime you increase your voltage, you're lowering your current load in terms of per active. So here we are, guys. This was gigantic. Remember, I think it was the second or third slide that looked at the evolution, and it showed 550 megahertz. And I said this was the introduction of optics. So here we are. This is exactly what I was talking about. We've got our head end. And we've got a string of coax and coaxial amplifiers. And if you multiply what you see here drafted times 5 or 6, you'll be out to 30 plus actives in what we call a trunk cascade. And prior to optics, this was how we reached the further extremities of town. We had miles and miles of coax. True enough, it was probably larger coax like 750 or 875, even some 1-inch. But that still means you've got, a trunk amp every couple thousand feet at the most. And as we know, these trunk amps, they work really great, but the more of them you put in cascade, the worse your performance becomes, the more distortion you're accumulating. And essentially you get to a point where the last few subscribers off of a long stretch of coax, not only the trunk being 30 amplifiers, but then now you get into your distribution, and there could be who knows how many line extenders before you actually get to a neighborhood that might be on the far ends of town. And boy, they're, sometimes you're sent out there as a technician and their pictures aren't that great, and there's not a lot you can do about it. I remember many of those types of service calls. So when we got to 550 and we introduced optics, now we replace all these trunk amps on this trunk line with a fiber link, an optical link. And now that means we're on glass all the way from the head end, maybe 12, 15 miles or so. We get to what we call a node, an optical receiver. And now this distortion with these amplifiers and all that starts at this point, not at this point. So that is a huge improvement in performance, huge improvement in distortion, much more reliability. You're not relying on 30 amplifiers to all keep running and not have any kind of a problem to keep your network up and running. Now you're just relying on a single piece of fiber optic to get to this node. As long as this node is running fine, boy, you've really done it. You've really improved your network. So that's why I say that's probably the most significant step in network evolution to date. So with that being said, I'm sure many of you know this, but there might be some on the call who aren't quite aware of how this works with fiber links from the head end. So we have our head end, and we have fiber cable that we've placed. And just like coax, along that fiber, we splice at certain points, and we get into that fiber, and we bring out different fibers. We go to different nodes. We go to what's called node serving areas. We have different types of architectures when it comes to HFC. One of them is what we call node plus zero, meaning that it's a node and there's a bunch of taps and passives and splitters and so forth, but there's no actives. It's just the node. Because it's just the node and we don't have the opportunity to amplify the RF after it leaves the node, we're kind of restricted to how many homes we can pass. I would say 120 passings is pretty hopeful. A lot of that depends on the frequency. Obviously, the higher the frequency this design is, the less homes you might get. In other words, if this was a 750 node plus zero, as far as 750 megahertz, you might get your 120, maybe even 130. But if you increase this to 870 or 1 gigahertz and it's node zero, you might be 100 or maybe even slightly under 100. It just depends. As we know, the higher we go in frequency, the more attenuation on cable, the higher insertion losses we have through taps and splitters and so forth. So that does affect what you can do at N0. But we go back to our node areas at N4, N6, where we're now allowed to place actives. We can place actives. It's probably what most of you guys are used to seeing. We can really do some damage. We can really get out there and reach a high passings count, 750 homes plus on a node plus 6 network is not that unusual. We're actually up around 1,000 homes in some nodes. So that means we've reached 1,000 people in this one single node by, within this node, one single node area, sorry, with this one single optical receiver. So we just duplicate that. We duplicate that all over town. That head end serves who knows how many different nodes. There can be quite a few in a large city. So now we jump back. We were going down that slide and we got to 1.2 gigahertz, and I mentioned OFDM. So again, here we are. There is a very kind of simple way to explain this. I say 10 pounds of throughput in a 5-pound bag. I could put it a different way. Let's say you had a water tank that holds 100 gallons of water. And at the base of that water tank, you have a 1-inch diameter conduit that's 20 feet long. So you open up the valve to let the water out through that 1-inch pipe. And let's say it takes 20 minutes to drain the 100 gallons of water. Okay. So we add OFDM to that equation. And what we're doing is we are allowing several bits to be sent in parallel of data bits or bits of information in parallel or at the same time instead of just one after the other. So we've now increased our water flow. We've increased our throughput. If we added OFDM to that same water tank and that same 1-inch pipe, we could possibly drain that tank maybe in 10 minutes instead of 20 minutes. So we're transferring data at a much faster rate. And this is generally used on our downstream. This would be basically the CMTS sending information to the modems at a much faster rate than it would be if we weren't deploying orthogonal frequency division multiplexing. So that's kind of a simple way to explain the advantage of OFDM. You've probably heard some of the engineers in your company talking about that. This is basically what they're saying. So then we also have what's called OFDMA. It's very similar to OFDM, but it's 3 times the throughput of OFDM. So it's like supercharging the OFDM. We typically use it in the upstream. I'll explain that in a minute. But at the present time, let's take our water tank situation again. And instead of it taking 10 minutes to drain, we're going to now drain it in 3 minutes or 4 minutes. So what we're looking at here is kind of a time domain. OFDM processes each user at a time, more or less. OFDMA can allocate subsets of carriers to different users, and we can process multiple users all at the same time. So over here, you've got a dark blue user, sort of a dark green, a lighter green, and sort of a yellow-brown user. Over here, you've got them all intermixed with each other because they're all being processed at the same time. So through this time domain right here, the throughput, the transferent of all these different users is going at 3 times the speed. And again, this is generally used on the upstream. We'll take a look at that. If we were to draw it out, it would look something like this. You have your head end like we always do. We have our optical link like we always do. I'll explain what this RPD is in a second, but we have our node basically like we always do. And now we're transferring OFDM on the downstream to the customer. And when the modem requests information or requests access to the CMTS, that's done with the OFDMA going back upstream. So the requests on the downstream is far less than the amount of requests we get on the upstream. So we have to increase that, and this is basically how we do it. Okay, so we're going to talk a little bit here about remote PHY. Brought that up also on that second or third slide when we first started. You guys have probably heard about DAA, distributed access architecture. Simply put, this is basically moving the physical layer, such as the CMTS, from the head end to the edge of the access network. You can kind of think of the edge of the access network as the node. We talked about node serving areas. The node in that node serving area could be considered the edge of the access network. What this is doing with R-PHY, it's taking the CMTS from the head end and moving it out here to what we call an RPD. It's now a remote PHY device. That's why it's changed from being called just a simple node to a remote PHY device. It's basically doing everything the node has always done, except it's now relocated the CMTS much, much closer to the subscriber base. So you can imagine if this fiber link is 15 or 20 miles long, you've just eliminated 15 or 20 miles of fiber optic cabling in terms of the CMTS reacting to the modem request and sending grants to the modem. So that has really helped. That's really improved our access speeds, our bidirectional, our up and down. Anything you would request in your home, you want to watch something on HBO or Showtime or whatever it might be, or you're ordering a whole bunch of stuff on Amazon, it's going to happen a lot quicker now because we've relocated the CMTS. So that's remote PHY. We call it R-PHY, and the device is now named an RPD. So we also have remote MAC-PHY. That was also on that second or third slide. And it's also a form of DAA, distributed access architecture. MAC-PHY has an advantage over R-PHY in that MAC-PHY also handles CMTS in the same way basically as R-PHY does, but it also handles the DOCSIS MAC. So there is an advantage to remote MAC-PHY. We call that device now, it's still kind of the same thing, functioning, is doing the same thing your node has always done, but now it's a remote PHY, a remote MAC device, I'm sorry. So that is causing the physical layer, R-PHY, physical layer transceiver connects the coaxial interface of the Ethernet. MAC is a media access control, which controls the physical layer, but also controls the transfer of data from the PHY. So it's a little confusing, but you may have heard some of your engineers in and around your company talking about some of this stuff. And this is basically what they're saying. They're just saying we're really going to enhance and improve the edge of the access network. And it's done through both of these PHYs. Essentially, we're eliminating the need for analog optics. It's still optics, but it's gone from analog to digital. And this is going to produce an inherently cleaner RF signal. So basically, to sum it up, it's this last paragraph. As we go higher in frequency to increase bandwidth and data capacity, we need to increase operating levels and gain associated with HFC electronics. Unwanted distortions, performance are products of these necessary power increases. It can't be avoided. Anytime we increase gain or raise the levels of our actives, we want more power. We want to get there quicker, better, faster. We're talking about physics. And when you do that, a lot of times you're quite naturally, you're going to have a few more distortion products to deal with. It's just part of it. But the advent of PHY technology helps to reduce those unwanted performance products by the elimination of analog optics. So it's quite an improvement. So now we're talking the very bottom part of that slide, as far as the evolution goes, was 1.8 gigahertz. And so here we are today. This is something a lot of broadband companies are looking at. This is a huge increase in bandwidth of the usable downstream and upstream spectrums. We're gonna really optimize that coax and fiber network capacity when we get to 1.8. We're really going to push it. So in terms of 1.8, we've got a usable downstream of 54 to 1794 megahertz. That is giant. That's like a 2-lane highway being expanded to a 6-lane highway, and can handle a lot more traffic, a lot more cars, a lot more volume. We're really doing something here. So it basically what it's going to do, the CMTS again is being relocated through the RPD. But when we get to 1.8, we're probably going to incorporate an RMD. So now we've got the CMTS and the DOCSIS MAC both in the RMD. It's basically going to replace the existing node as we know it today. So we've talked a lot about coax. We're talking a little bit about fiber. I'm going to probably speed this up a little bit because I noticed that I'm at about 4:46. So one of the biggest advantages of the HFC plant is we've already got it out there. It's already running. It's already working. It's already producing a profit. If we want to upgrade it, we're going to use a lot of the same components. We might replace some of the electronics, but the cable is already there. So there's a huge advantage to continuing to look at upgrading the HFC plant, which a lot of us are doing. If we want to replace the HFC plant that's existing, we do have to consider that it means overbuilding, activating, removing the previous infrastructure with the new. Essentially, all the coax-related HFC network components are replaced with purely fiber cable optical components. You can imagine that could be a little pricey to do that. So that's why a lot of companies take a real good hard look at continuing the use of their HFC or continuing to upgrade and enhance their HFC networks. If we build new fiber to the home, that can be a little bit of a savings over building a coaxial network. Fiber generally is not quite as expensive as coax can be. Depends, there's a lot of variables there. If there's no fiber or if there's insufficient fiber in the area, it can mean new fiber placements or augmentation of the existing fiber becomes necessary, or we have to do wave division multiplexing to advantage the use of the existing fiber by the use of multiple wavelengths on that existing fiber. So there's a lot of variables that say, yeah, we can go FTTH, or no, we're going to stay HFC. And these are just some of the considerations that an operator really has to take a good hard look at. Fiber is similar to HFC in the fact that once we break it down, we have what we call our fiber serving areas. There are also segregated network footprints called FSAs. They can be as small as 72 passing areas, just like an NO node, an N+0 node, or upward of thousands of passings in a single FTTH area. It just depends on the type of architecture we're going to use in the fiber. Just like HFC, there's multiple architectures to consider, depending on what it is you need to achieve, what you need to, what is your competition doing, and all that sort of thing. So just like anything else, what are the costs? What's the return on investment? These are all huge considerations. In an FDH, we'll have an FDH cabinet, we'll have optical splitters, we'll have our OLT, we'll have optical taps, we'll have splice cases, we'll have all those things to make that network function. These are some of the pictures of some of the fiber components. These are some large FDH cabinets. They go from small ones to very, very large ones. I worked for a company once that we had some 6-bay type cabinets custom built. They were air conditioned, they had gas generator backup, and we served over 4,000 homes from these types of cabinets. We were pulling in huge fiber counts, true enough, but it can be done. So this is a typical fiber optic splice enclosure. Your fibers come in here, they splice in these trays. This is fiber cable itself. This is an optical tap. They look much, much different than an HFC tap. This particular tap would be like an 8-port tap in terms of fiber. I don't know if anyone's seen, this is just a very average typical fiber layout. This is kind of what it would look like on a map. You have your storage loops. Fiber always has to have storage associated with it. You have your splice enclosures, which is what we looked at on that previous slide. Every cable has a unique ID, no matter how long or short it is. And these are your fiber counts. That means this is a 24 count fiber. These are 144 count fibers, and so on and so forth. So this would be basically a construction ready type of print for a fiber network. This is the distribution in a fiber network. We have our splice cases here. We've got our optical taps. These are actually, what they are is actually splitters. There's a discrete fiber. This happens to be a distributed split design. So there'll be a single fiber that came into this optical split, 8-way splitter, and it would be spliced to these ports. So there's a lot of detailed splice documentation that's needed and necessary to be able to splice this network up. But this is what it would look like. It's similar to HFC, but a little different. So that's really it, guys. I think you can see we've gone a long ways. We've come a long ways. It's sometimes very difficult to keep up with the technology. There's a lot of competition. We've got competition between other cable companies. We all are in competition. The telephone companies are competition. Even power companies are competition for video and data and internet and voice. I mean, they're in it too, just like we are. So there's a lot of competition out there. We've seen where we combine multiple technologies when we're going to upgrade a legacy infrastructure. We push those networks to their limits. We push them as far as they can possibly go. And then we get ready for the next time. So I just want to say, I think we've all chosen a great career path. It challenges us every single day, and it's exciting to be part of it. And I want to thank everybody for listening in and being part of this presentation. Thank you very much.
Thanks, Keith. Yeah, it doesn't look like there's any more questions, so I guess this will conclude the webinar. Oh, we got one more. They're coming at the last second. Will extending the spectrum to 1.8 gigahertz really work? Do we have to double or triple the number of amplifiers? Are the new amplifiers, or do we have to double or triple the number of amplifiers, or do the new ones have higher gain?
That's a really good question. The answer is no, we don't have to double or triple the amplifiers. There are some instances in some nodes that are going to upgrade to 1.8 where we may have to add an extra active or possibly two on certain legs, but know that the manufacturers are well aware of the higher gain that they have to produce, the things that they have to do to these 1.8 electronics to make them play ball in the existing network as much as possible, to avoid adding any additional actives, and also to try to avoid relocating any of the existing actives. That can be costly. So they're well aware of that, and they're working around all those parameters to make it so it's as much of a drop-in as it can possibly be.
Cool. Anyone else have any other questions for Keith? Somebody said, why not just make the whole spectrum OFDM? I believe that's the direction we're going with DOCSIS 4.0.
Yeah, the whole spectrum I don't think will be, but the certainly a significant portion of it will be.
And then we have another question: why not use OFDMA on the downstream as well as the upstream? That's a good question.
You know, I've had that question too, and I'm probably not the best person to answer that. If there's someone else on the call that might know that answer, I don't know if people can speak on this, but I don't know that I have that particular answer, to be honest with you.
Okay, and then there's one more. Any chance to speak to EPON?
Not really on this particular presentation.
Okay. I think that's it for questions. Yeah, thanks again, Keith. You did a great job, and thanks everyone for attending. And this will conclude today's webinar.